This is online course, so I will prepare slides in advance. Mostly I'll be using slides, and then I would annotate by writing on the slides. And hopefully by recording the lecture, you'll be able to review. Okay, so welcome again. So this is 682. It's a special topic in solid state physics. And this semester, the topic is quantum information science. So I'm your instructor, Tu Wei. So this, I'm summarizing what I have on the syllabus, but you can see from this web link, that's where the course website is. Can you all see my mouse or cursor?
Yes.
Okay, good. So this is a survey of really fast evolving field of quantum information science. It has a lot of topics. It goes from the ancient history of quantum mechanics through the most recent development. So my goal is to cover essential knowledge of quantum information science and help you to bridge the gap to the current research activities, or maybe the news that you hear about company doing quantum computing or software, etc. Since it's a solid state physics course, I would put some emphasis on the solid state platform of quantum computer, like the one that IBM is using. I would also mention other system because it's almost impossible not to mention any other system involved in quantum information. And more interestingly, I would actually teach you how to do programming on IBM's quantum computer. So stop me anytime if you have questions. So maybe some of you have seen this slide. And this is taken from Wikipedia. This is about National Quantum Initiative Act. It's actually signed into a law that would give US a plan to advance quantum technology, in particular quantum computing. So this is the course that this is going to talk about a lot of development, why quantum computing is important, and also its fundamental background behind that. But I think if you, for everybody, layman that read this news, this implies that there will be more job opportunity because there will be a lot of money, dollars invested on quantum information science and also technology. So including research and industry. So I'm here just list 3 learning outcomes. So what you would expect if you have completed this course, you will be able to understand the physical principle of quantum computing and how quantum algorithms work. For example, you may have heard Shor's factorings and global search algorithm. So these are the basic but also important algorithm. And you will also be able to understand the basics of information theory, which is usually not taught in physics, and their relation to statistical mechanics and quantum entanglement. And the third learning outcome that I list is that once you complete this course, you will be able to understand the working principle of some of solid state qubit, and you will be able to do simple programming on IBM quantum computer, and some of which are available publicly. So below I list a few quantum computer from a few companies like the IBM, Intel, Google, Rigetti, D-Wave, and IonQ. There are booming number of startup company. You name it, Amazon, they also is investing on quantum computing. Honeywell, Alibaba and a lot of company. So I think this is the time for quantum computing and also the AI. So these are, I think, the most important technology advancement. Okay, so I would talk about grading. Mostly will be homework. You see homework consists of 50%, but the purpose of homework is to help you understand the content of the lecture material. So these will provide opportunity for you to work through some of the stuff that I go over or maybe gloss over, and you'll be able to fill in the gap. I hope you can participate, even though the lectures will be recorded, but it's actually useful if you participate and have discussions. And it's really important to be learning actively. If you just watch the recorded video passively, you probably will not be able to learn. And if you participate, you can ask questions. So since it's online course, it's not an ideal situation to give exam. So there will be no exam in this course. So maybe that's a good news to most of you. But I would devise some midterm report. It could be a short take-home exam, or it could be just a report that you write on what you think about some of the interesting topic. The idea is to gauge how you are doing. And then there would, in the end of semester, there will be a final presentation. So we have about 29 students enrolled. So I need to think about how much time each of you can take, maybe 10 to 15. And then we would devote maybe the last 2 weeks as a final presentation. And I also would like you to have an end semester report. This is really just maybe at the end, you sort of reflect what you have learned, what are the most exciting things, or maybe what are the most boring things that you have heard. Regarding homework, I hope that you can turn homework on time. So there's no late homework. Homework will not be difficult. So in fact, I actually post the first homework to the Blackboard. But if you really have problem, you need to let me know maybe 2 days in advance before the deadline. Maybe I pause here to see if you have any question. Okay, so but this is how I will grade this. Yes.
Is the homework gonna be weekly?
I try to give homework weekly because some of these will just help you to fill in the blank, go to similar example. So it's because the topic would change from week to week. If you miss the homework, maybe you would miss some understanding. So it's, but I try to give really simple. You could probably do it in half an hour. But if later you feel that it's too much to have weekly homework, let me know, I can adjust. So I don't know how your schedule, how busy, everybody has different schedule. So, but let me know. But I try to give you really simple things that if you go through them, you actually have more feeling about the content. Does that answer your question?
Yeah. And are there gonna be solutions or
solution? Yeah. So after you turn in the homework, I will post the solutions. Are everybody familiar with the Blackboard? So I'm going to, I already posted homework 1 in Blackboard, and then the submission of homework is also through the Blackboard. You upload your homework. So you can, if you can write on the PDF file or it's okay, you write on paper and then take the picture, but the idea is you upload to the Blackboard so that I have a place that I can look for homework. So there's no TA, so I'll be grading the homework. Any other question? Okay. If you have question, you can also post in the chat, and then if when I pause, I would take a look at the chat. Textbook, there's no required textbook. So I will give you the slides, and if I write anything on that, I will keep the annotations so that you have that afterward. But there are a few recommended textbook. The first one is Nielsen and Tran, Quantum Computing and Quantum Information. I think this book has a lot of material, but it was published around 2000, so a bit outdated. But this book has about 700 pages, so it's a huge book. The second one is a thinner one, it's about 300 pages. So it's an introduction to quantum computing by K. Laflamme, Moscow. The third, I think you can see these two in the recommended in the solar. A third one is online collection of lecture notes by a famous scientist, John Praskill, in Caltech. So you can click the link. The link is also on the course website. You can download the lecture notes. The fourth one is it's not about quantum computing, but about quantum physics. So I recommend Feynman lectures, and these actually can be read online. The fifth one is actually another online book. This is a Qiskit book. Qiskit is a software framework developed by IBM, but there is a book edited by the community about quantum computing and also how you use the Qiskit. So these are the 5 recommended one because my topic is not contained in a single book. So I would post the slides, and if I feel that a particular section or link of paper, then I will put that in the website. Most of you may not come from physics, so you may also wonder what mathematics is needed. There is a short book, online book by Dr. LaForest at University of Waterloo. Basically, what you need is linear algebra, but I will review a little bit later. So these are the cover of the books that I mentioned: Nielsen and Tran, K. Laflamme, and Mosca, and Feynman's book. This is an additional book that I recently found. It's a more modern way of learning quantum computing by Jack Hillary. You can check that out. This is the link of Praskill's book. Any question so far about the textbook? Okay. Yeah, this here is the website of the Qiskit book. So this is learning quantum computing using Qiskit. So it covers some of the material content that I will use. So I would use some of the material in this online book. And if we are dealing with codes, I would use some of those on this book as well, and others that I wrote myself. So you don't need to worry about coding. It's really simple. We will deal with that later. Okay, so there's a quote that I like from this Qiskit book. It says, quantum computing is the perfect way to dip your toes into quantum physics. It really is, because now we have a really new language to learn quantum physics. It's through quantum computing. So, and it continues to say that it is still the core concept from quantum physics into their simplest form, stripping away the complication of the physical world. So in order to being able to understand quantum computing, you don't really need to study a lot of quantum mechanics. So I would say the first chapter of a typical quantum mechanics is already enough, but I'm going to review the material. Okay. I'm going to show you just the list of topics that will be covered, but I'm not going to into the detail because we will be doing that. So I hope that this will not frighten you, but this just shows that there are diverse topics that will be covered. So from basic quantum mechanics, qubit, Bell inequality, teleportation, and superconducting qubit, other topological ones, and quantum gate, programming on IBM, and how you deal with error. And there's a interesting way of doing quantum computing is to do braiding using the so-called anyons. And it turns out this is related to topological phases. So we're going to cover that. And there are also other ways of doing quantum computing. So, and one of the key notion in quantum information is entanglement. So this actually has become a universal language. It's not only used in quantum information, it's also used in high energy condensed matter, a lot of places. So I would also talk about algorithms, for example, quantum Fourier transform. I will also talk about quantum communication. So you can see there are diverse topics, but any of these, we will go into detail, and the math will be self-contained in this course. Okay, so let me pause here, see if you have any question. So if not, let me see if I could do the polling. Oh, sorry. Let's see, okay. Maybe I stop sharing and then do the poll. Okay, so these are the polls. I hope you can see that. Just take a few minutes. I know some of you register, maybe most of you register, but there are other people that would like to order this. Okay, so I think 86% of people have voted. So let me just end the polling. If you would like to fill in the answer, please do it now. I'm going to end the poll in 5 seconds. Okay, so I'm end polling and share results. Can you see the results? So because this is a course offered in physics, naturally people from physics take this one. The next large population is from math, applied math. There are also people from CS. I'm surprised I don't see anyone from chemistry, nor ECE, and maybe a couple people from mechanical engineering. I don't see other. So as I said in my course website, I'm going to design this course so that students from different STEM field will be able to understand using really minimum mathematics. So new mathematics I'm going to introduce along the way. So this is the first poll, and the second question is, what do you expect from this course? So about, okay, this is because you can view multiple selections. Yeah, 66% says answer I'm curious about this and just like to know more about. This is fine. I mean, everybody has different motivations. As long as you participate and enjoy, I think that's the most important. So second group, I want to apply this quantum information building to my research. The third group, I'm thinking about getting a job in industry. So actually this is a lot of people that I know who graduate actually from their PhD actually went into industry, and there are a lot of opportunities. Some select, I don't have any expectation, just meaning what you have got. Okay. So I've closed the poll. Let me share the screen again. Any question before I move on? Okay, so since this is an overview, I'm just going to select some random but interesting topic just to give you a flavor of what's to come. So I call this appetizers. So I'm going to show you two interesting setup. The first one is so-called double-slit experiment. The second one is called Mach-Zehnder interferometer. Let me go to the next page. Yeah. So I'm sure many of you have seen the double-slit experiment, right? So it's a wave and have interference pattern going to two slits. It happened for classical wave, but even for tiniest particle like electrons, it would also have interference pattern like this. If you are shooting electron or uses or photon, they share a similar pattern. But very interestingly, for a quantum particle, if you know where, for example, electron go through this slit or go through that slit, you would not be able to see this interference pattern. Instead, you will see interference pattern erased, like a classical particle. If you're shooting a bullet, that's what you see, the distribution. Okay, so how do we understand this? Anyone want to share? How do we understand this phenomenon? Okay, so the first one shows interference, right? The second one, there's no interference. But how do we know when we'll get interference and when we'll not? So the first one is like wave have interference. It's basically you take some two of the wave that come out from these two, add together, and then evaluate that strength at this location of the screen. This one is particle-like. It's really adding the probability separately. So apparently this one does not have interference. For interference, what I mean is if you take the two wave, there is a cross turn. Here there's no cross turn. That's one understanding. Another way is to use a more modern language. If I know the so-called which way information, I know the particle go through this, then there is no interference. If the particle can come from either this slit or that slit, and there's no way in principle to know where the particle come from, then you will get interference. So this is very strange, but this is the way it operates. So you've seen this double slit experiment, but when you think about really tiny particle like electron, individual electron, it interferes with the cell. Okay, any question? So now I'm going to sort of change this slightly. I'm thinking about I'm sending in light or photons. Photon has the so-called polarization, right? It's the electric field oscillating, the direction it oscillating like horizontally. Now, if I use something called wave plate that rotate the polarization into a vertical. So then the light coming out from the two slit would come with a tag. It's either horizontal or vertical. I already showed you that actually you will not see interference, right? This is because the which way information is revealed, right? If my detector, let's say it can resolve the polarization, then I know that if I detect a vertical polarized photon, it must come from this. If I detect a horizontally polarized photon, it must come from the lower slit. So if you have a which way information, you will be able to know that there's no interference pattern. There's no fringes, right? Okay, I hope you get this. But now I can ask myself, under this setup, is there any way that I can do between the photon coming out and the screen so that I can actually recover interference, fringes? Who think this is possible? You can raise your hand. I think there's a raise hand function. Okay. Somebody will raise hand, think this is possible, but how do I recover interference fringes? Right? It looks like I would be able to know where it comes from by detecting its polarization, right? If I have a way to erase the which way information, then I will be able to recover the fringes. The cool thing, this is related to some of the 3D glasses you use in the movie theater, using polarizer. So suppose we put a polarizer here, right? The polarizer will filter out. So vertically polarized light, because it's not orthogonal, not complete orthogonal to 45-degree polarizer, some of the component would get filtered out, and the light that passed through will be polarized along the 45-degree. And so is the case for the horizontally polarized light passing through. they become the same light. Of course, some of the light get absorbed, disappear, because the polarizer only allowed part of light to go through, and some may be reflected. But after the polarizer, between the screen, there is no information. There's no way you can figure out, I see this is 45 degrees, but I don't know where it comes from, the vertically polarized light or the horizontally polarized light. So there you go, you will see fringes, right? So this is amazing. This really just by some kind of Gedanken experiment, by thinking, you can actually get this interesting result. So you could also put the polarization or polarizing beam splitter or polarizer at 135 degrees. Then you will see the fringe pattern is complementary. It's a complementary. So here I show 45 degrees. Let me just see if I could draw. So I show the 45 degrees, but if you use the one that's 135 degrees, so sort of complementary to that, you will see a fringe pattern that's sort of complementary, in the sense that when you add the two, it would just recover that. So in a sense that this polarizer is filtering out the interference fringes. And there are two independent set of fringes. If you add them together, you actually get this no interference here. Okay, any question? I hope that this example intrigued you, that it's really a strange world in quantum mechanics, and there are a lot of even stranger things that can happen. Quantum computing is one of the applications of the strange quantum world.
I have a question.
Yes.
This one polarizer should be exactly 45 degree, right? If it's a little bit noise, 45.001, then you can distinguish these two from V or from H. Then there will be no interference, right?
That's a good question. So it does not need to be exactly at 45 degrees. If you sort of deviate a little bit, maybe 46 degrees, the projection of V to the 46 degree is slightly different from the H to the 46 degree, but it's so tiny that you would probably change a little bit. So you don't need to be exactly 45. So, but this actually answers your question in a maybe more general way. So for the light that comes out from the slit, I can put a tag. So I just use psi 1 to denote the light coming out from here. Theta 1 is the angle of polarization. And similarly, psi 2 for the wave coming out from here. And then theta 2 is a sort of a label for the polarization, okay? So if I remember before I had this, right? I have these wave light and particle light. And actually from here, you can see both of them appear in one equation. For example, if I sort of take absolute value and square that, I have the diagonal term psi 1 squared, psi 2 squared. Doesn't matter at this point what the psi are, it's just some probability. Psi is an amplitude. But you see there is a cross term. So when you square this, you have cross term, psi 1 and psi 2. And also, because the label theta 1 and theta 2, they also need to also take the inner product. And if these two are orthogonal, right? If these, you know which one is which, like in this case, V and H, this means that this term is 0. Okay, so you get a particle-like behavior. But if you use the same for example, here, H, there's no a wave plate to rotate that, then this is 1, and you see the interference. So in the same way that when you go through that, the filter would change maybe the relative amplitude a little bit, but the light comes out is always the same angle. So this term would be 1, except that the amplitude may be changed a little bit. So it will still have interference pattern. Okay, does that answer your question?
Sure, thanks.
Okay.
I have a question.
Yes.
Not a question, just a confirmation. You were explaining that I didn't get this part of 45° and plus 35° when the two interferences are added.
So I'm saying that the 45°, I choose this 45° polarizer, right? And let me say this way. Just some 45° polarizer, and then another 135° polarizer, right? A light can always decompose into any basis. Okay, so it could be some component along 45°, another component along 135, right? So it's like a vector you can decompose into two different directions. And my point is that if I choose this, then I get a pattern, right? If I choose this, I should get a different pattern, right? But I know that when the light comes out to here, if there's no polarizer, I get this pattern, right? So I know the end sum should be the 45° interference pattern plus 135° interference pattern, and then adding up to this.
Okay, yeah.
Does that make sense?
Yeah.
Thanks a lot. Okay. At this point, you don't need to understand in the most rigorous mathematical way, just intuitive understanding that a light can be decomposed into two directions of the polarization. If I filter out one direction, there must also be another direction. It's reflected somewhere or get absorbed. But if I choose to do the other way, I get another pattern. And I should add them up to the case where there is no filtering.
Okay, got it.
Okay.
Thanks a lot.
Okay, thanks for the question. So the next one is so-called Mach-Zehnder interferometer. I think this also gives some strange phenomena from quantum mechanics. So I have a setup like this. On the left, there's a light go through a so-called beam splitter. It's split into two. And these are mirrors that reflect light. At the end, there's also another beam splitter. It allows light to go through, reflect. And I have a setup like this. And I imagine that in some perfect scenario, I assume that if I place a bomb here, if a light go through and hit the bomb, assume that it would explode immediately, 100%. But light could also go through this path and maybe also here to B or detector A. So my question to you is that, what is the probability that the bomb explodes? Assuming this is a quantum particle, and what is the probability that the detector A and B clicks? So let me say a little bit. I'm assuming that if it's a quantum particle, light always come out here. Okay, I would do some math for you, but I'm saying that suppose I start with this scenario, and I imagine I put a bomb here. What would be the probability that this bomb explode, assuming the photon has 50% go through, 50% reflect at both beam splitter. So what do you think the probability that is for the bomb to explode in the second scenario? You can think in terms of the probability, how much probability would the light end up here?
So if it's a 50-50 split, then maybe 50% probability?
That's right. This is 50%. It's 50%. And what is the probability that the detector will be able to detect the light at B here or the light at A? What do you think?
Is it again a 50% split at
So there's a 50% here, right? So the other 50% should go here.
and then when it hits the splitter between A and B?
Yeah, right. So then there should be 25, 25 here, right?
Yeah.
Okay, so that actually is the correct answer, but I'm going to show you how we do that using the interference that we learned before, but I'm also made the conclusion by comparing the two scenarios. Here there's no bomb, right? Here there's a bomb. And you can see the difference is that, okay, 50% we're unlucky, so the bomb explodes. Suppose we are trying to detect there's some sensitive object there. Half of the time, we're unlucky, but you see that 25% of time, we know there is a presence of a bomb, right? Otherwise, the light could not have reached B here. That makes sense? Because I'm measuring my starting point is that the light always go to here. So I would give you calculation that shows that we can do this. So, but suppose now I put a bomb here and the bomb does not explode, and you will see 25% of time you will see this detector click. So then you know there's a bomb, right? Isn't that weird, right? If I put a bomb, and then if I see a light here, then I can infer there's an object here. Okay. So this is really the consequence of quantum mechanics. And we can understand this using interference. But I'm going to contrast with the classical, let me call this a pinball. A pinball comes here. The flipper will flip 50% up or 50% through. So I'm going to assume it go through 50% and reflect 50%. So we know how to do the classical pinball. So the probability of a pinball get to A is it has to reflect here and then go here, or it go through here, reflect, and then reflect, right? So okay, this is really a bad handwriting, but it shows the path. The pinball can get to A, assuming now it's classical. So I'm just counting probability. So I have 50% through here, another 50% go through. This is what's indicated here. I could take a second path. It's 50% go through, and then 50% reflect. So I add up these probability, which is 1/2, okay? And then we could also, do the same calculation for the pinball to get to B. You see that it reflect and then reflect, or it transmit and then transmit. You calculate this probability. It's easy to see that this is 1/2, okay? So I promise that I'm going to explain to you how am I going to do the setup so that I end up at A always. So I'm going to introduce a special rule for a quantum pinball, it goes through, when you go through, you would use the amplitude. Remember our psi 1, psi 2, we'll use amplitude, 1 over square root 2. If it gets deflected, I put an I. I hope you remember what I is. It's the square root of -1. So then we can do the calculation again. What is the probability that a pinball gets through A? The same argument, it should reflect, transmit, or it should transmit and reflect. But now the calculation is a slight different. We need to use this interference. So the way we do that is for the path 1, it has amplitude, get reflected, and then get transmitted. So you just multiply them together. There's a second path. It goes through with 1 over square root 2 amplitude. It reflects with an amplitude with the I here. And then you take the absolute value and square that, you get 1. So it always go to A. I can also check it should not go to B using the same calculations. So the same calculation, you need to consider the path being reflected, or to transmission. So how do we do the calculations? We put everything in the absolute value symbol. It reflect, so has an I here. Reflect has an I. Both of these are transmission, so there's no I. And you see now the square root of -1 comes into play. This is I times I, so it's -1, cancel this out, so it's probably 0, okay? So now we have an understanding. I mean, you could also do the calculation using interference to conclude this. But since there's only one path to get to the bomb here, there's only 1 over square root 2, but you square that, it's 1/2. To get to A, there's only one unique path, right? Like reflect and then transmit. To get to B, there's only one unique path. Yeah, when you have unique path, there's no interference. You can just use the classical reasoning, right? So now you understand that by putting an object here, it sometimes can allow you to detect, right, without exploding the bomb. This is also called interaction-free measurement. It looks like that my light, my photon does not interact when it comes out here. It means that it seems to indicate the light does not interact with the bomb. Otherwise, it should have exploded. But it ended up here at port B so that I can detect, I can measure the presence of a bomb. So this seems very weird. Any questions?
So is there a method to lower the bomb explosion probability to arbitrarily small? I heard there is a method.
Yes, there is a method. You need to use sort of iterative way. There's an iterative way that you sort of encode another interference interferometer here, and you do many layers, and then you can actually make it arbitrarily small. Yeah, I can, if you can remind me, I can try to find a reference for that.
But the precision is preserved.
The precision? You
Yeah,
need to very precise
the precision to determine 1 and 2. They are still very clear.
Yeah, so there would be 100% you can detect the bomb. In this case, we only have 25%, but there is a way to actually increase that. Okay. Okay, so that's the first two appetizers. And I'm just going to flash that this is one of the important algorithms we're going to cover later in the course. it's about factor a large number. For example, if I give you this, I think it's 110 digit number, can you tell me that it's a prime or not? I think primality test is simple. You can check it's a prime or not. But if it's not a prime, can you factorize this number? And this is what Shor's algorithm is about. So, okay, you can check that if you multiply these two back, it should be this number. But figuring out the factors are not so easy. And in fact, this is used in the so-called RSA encryption. So if we have a quantum computer, we can actually factor a large number easily. It's actually almost exponentially faster than the current classical algorithm. But I want to emphasize that it only uses really simple rule of quantum mechanics, superposition. You've seen that from interference. In unitary evolution, you actually also have seen that it's the evolution of a system. It looks, for example, the light propagate, it's also unitary evolution. And measurement, we've seen that we detect whether the light goes through this or not. So in fact, Shor's algorithm only use these three rules to actually allow exponential speedup. But you have to wait a little while because we're going to cover that later, much later in this semester. Okay, and I also mentioned at the beginning that IBM actually offer cloud quantum computer you can use. I think this /shop is quite old. There are also other machine that you can use. If you do not have an IBM Q account, I would encourage you to create one. Although in this course, you don't really need one. I'm going to provide you the Jupyter notebook if I illustrate the code. But it would be useful that you can actually register an account. You can actually run on their quantum computer. It's not necessary, but it's encouraged that you can create an account. If you don't know how to do that, you can email me. I'll guide you through. But this is the link. It just create an account. You may be using your email and then create an account with the IBM. This is one paper published by IBM Group that they actually use quantum computer to do real molecule simulation. For example, they can simulate the hydrogen molecule, the spectrum. So the energy versus the distance between the two hydrogens. So this is lithium hydride and other. So of course, at the moment, the data is not so perfect, but there are improvements that you can make to mitigate error to actually increase the precision. And later of this course, we're going to discuss these applications. But I want to actually say this is actually not that difficult because a lot of programming power has been done by IBM. They actually package a different function together. It's really easy to really implement on that. In fact, maybe some of you know that IBM in the summer had a 2-week summer school, which was open to anyone around the world. And I also participate in the summer school. I listened to lectures and then also did their lab, programming lab. And I think more than 2,000 people also, at the end, they did a project on simulating this molecule. And they have the so-called Discord channel. You can see a lot of people, they are not even the scientists, they have almost zero background, but it's encouraging. At the end of 2 weeks, they were able to do this project. So I just want to say that you are more than prepared than in most of these people in the IBM summer school. Okay, so maybe I want to take some time to review the mathematics. This is really the minimum mathematics that I need. You need to understand, you need to know. So mostly this will be linear algebra, basically vectors and matrices. But for other mathematics, we will learn that along the way. So let me just review a little, just show you some of the math that you should know, right? So complex number, we see this I is square root of -1. You should know the absolute value. You need to know that how you take the absolute value of a complex number, its real part, imaginary part. We here use star to represent complex conjugations. The complex conjugation of I is -I, etc. And you have these Euler formula. E to the I theta can be written as a cosine theta plus I sine theta. I believe most of you have seen this, right? Linear algebra, it's about vectors and matrices. So for example, I list 3 vectors, 1, 0, 0, 0, 1, 0, 0, 1. You can think about a direction in 3-dimensional space. But here I actually, by reviewing the linear algebra, I want to introduce the symbol that we're going to use very often. It's called bra-ket. In this case, it's ket. So I just put some labeling here, but I use like this vertical and angular bracket just to give this a symbol, okay? So 1 meaning I have 1 here, 2 meaning the second location, 3 is here. So you know these vector form orthonormal basis. So they're orthogonal in the sense of inner product. So I'm sure you know the inner product. And in the quantum mechanics world, we often put a complex conjugation here. And in terms of vectors, this is a column vector. If you take transpose, it's a row vector. A transpose and complex conjugation is also called a joint or Hermitian conjugate. So these are orthonormal, meaning that they are orthogonal to each other. They are different. So this is delta ij, meaning that if it's if the indices, 2 indices are not the same, this symbol is 0. But if they are the same, it's 1. So I want to introduce the bra-ket notation. The way we write in quantum mechanics is we would put the vector on the right, Vj, we use this symbol, a ket, and then we use this as bra. So this is rewriting this using the new symbol. So this is a symbol invented by a physicist called Dirac. And so it turns out to be very useful. So, but it's really just a symbol help us to simplify things. So regarding matrices, the most important kind of matrices in quantum mechanics is a unitary matrix. So it's satisfied as U Hermitian conjugate times U itself equal to identity is also equal to U times U dagger. So for example, there's a matrix here, unitary matrix. You can verify it satisfies this. And in terms of bra-ket notation, so we will write U as a summation over I and J. And these I and J, ket and bra, this is just used as a basis, right? Remember, we use this as a basis for the vector. For matrix, we can put a double symbol here, I and J, to represent sort of the location of the component. So for example, I can put a I here and J here to sandwich this U, I will get a component. This is just a notation. So, but we'll be using that a lot so that you become a second nature. So if I multiply a vector by a matrix, this is the usual way to do that. And the ith component is basically summing over the jth component of a vector V, and then the second component of matrix J, right? So the way we write to get the ith component, we just, in some sense, we start with V, apply the matrix, and sort of project some kind of project to this component I. It's only a symbol at this moment. And you all know identity matrix is 1, 1, 1 in the diagonal. The way we will write bracket with all these symbols being I from 1 to n. And I'm sure you know trace. Trace is taking the sum of diagonal element. Okay. So once you have a vector for matrix, you can do something. So for example, I can define something, not the inner product, but it's the outer product. I'm not doing the inner product. I'm taking a column vector here and times the row vector by taking the Hermitian conjugate. So using this symbol is really easy to see, right? It's really this vector. Just flip the shape. This is called a projector. If you do the calculation, it's 1, 0, 0, 0. It projects to the subspace, or in this case, the direction spanned by this vector. Projector has the property that it's a Hermitian and it's square to itself. The thing maybe you have not done much before is tensor product or Kronecker product. By Kronecker product, I mean this symbolically. You take a vector, tensor product, another vector. The way to do that is list the component of the first, and then just put the second vector in. So this second component is 0. I put V2 here, but multiply. I put 0, multiply V2. So I get 0, 1, 0, 0, 0, 0. It's not easy. It's going to be clumsy if we have many of these, but in terms of the bracket notation, it's really just 1 tensor product 2, okay? In terms of matrices, you can also take the tensor product. It's really just taking list the component. For A is A11, A12, A13, etc. For each component, you just stick a B matrix. That's the tensor product. Okay. Just to review a little bit more about linear algebra, I think one important concept is the eigenvalue equation in particular for Hermitian matrix that would be of interest in quantum mechanics. A Hermitian matrix, I hope you have seen this. It's n by n. For example, it's n by n. Hermitian matrix is one that it's dagger, meaning its complex conjugation and transpose is the same as a cell. And the eigenvalue equation is defined as applying the matrix to a vector equal the vector itself up to a component, proportional constant. And this is usually called eigenvalue. V is eigenvector. Sometimes we call it eigenstate because when we use bracket notation, it in some sense represents a quantum state. Okay. And for Hermitian matrices, these eigenvalues are all real. And the eigenvectors, they can be made orthonormal. It's like just like the 3 directions or in 3 dimensions or any orthonormal basis. Or just like the horizontally polarized line, vertically polarized line. So they're orthonormal. We can write this way, but we could also use our bracket notation. If some of the eigenvalues are same, they are called degenerate, and they can be made orthogonal in that degenerate subspace. So I give you an example here. So this is actually three most popular matrices in quantum mechanics. It's called polymatrices. Sometimes we use sigma, sometimes we just use X, Y, Z. So these are, so I just leave this as an exercise for you to find the eigenvalue and the eigenvector. In fact, this will be listed in the homework. So here is time that I should pause and then do the pause again. Let me see. Okay, so having gone through this, I wanted you to check with yourself, how are you familiar with the background math? Can you do the poll? Okay, so most of you are very comfortable with, are there still people trying to do the poll? I'll give you 5 seconds. Okay, so I'll share the results. So most of you are very comfortable with complex number linear algebra, which is very good. Some fraction of you said that you learned it before and are comfortable using that. And for those that answer that you can look at the math and should have no problem, I think this is okay, but do practice a little bit more to at least should move your level to the second group, at least the second group. It's good that I don't see anyone saying that I'm a bit rusty, I have to spend some effort on that. But this, along the course, we will do some practice, but in real problems. But if you want to make yourself more comfortable, you should review. So I will share the result. Okay. And close this tab. Okay. Any question? So yeah, so I mentioned this really short books of mathematical quantum mechanics. It really just the linear algebra and notation of bracket. It's listed here. But in the KISSIC notebook, there's also an appendix that also review. Okay, but if this is really a useful resource, if you feel that you need to refresh that, please do that. Let's see, what do I have? Okay, yeah, so one thing I'd like to discuss is I like to set up an office hour. But it may not be easy to determine a time at this instance. So I'm going to send a doodle poll to only those registered students. Ideally, it should be days that are not Monday and Wednesday. So for example, Tuesday, so that you don't need to see me twice on the same day. But I also set up a discussion board in Blackboard. This is the first time I use that. I will see how it goes. But you can discuss among yourself, and if you have questions and maybe somebody else knows the answer, can reply. And from time to time, I would also check the discussion board and then answer some questions. Okay. I would keep the notation and start. Okay, any Any questions so far?
Yeah, Professor, I have a question. Will you upload your homework and solution on your course website? Since
Yeah,
I'm just on this course.
you're not registered?
Yeah, I'm not registered.
Then if you want, and maybe, yeah, I can post also on the course website, but I would add simple password just to protect the material from some of the website. They really just collect lecture notes, homework problem, and publish in some book, some kind of book. But I can also post on the, but I will let you know the password.
Okay.
Any other question? Feel free to ask. This is a course I'm excited about this because I've been doing research in this field for a long time. And finally, the department gave me a chance to share this with you. I think in Stony Brook, there are also other related courses. Some of you already have taken maybe one from IACS. EC also has a similar course. But I feel myself, I know the topic very well. So, but I like to encourage participation from all of you. Even if you're auditing, you can still participate. I think it's, I don't want to be just a one-man show, just doing here alone. But I encourage you to ask questions. It could be through the chat. Okay, I think there's some chat. Let me see. Okay, yeah, okay. People answer the question. Yeah. Yeah, okay, yeah. The bomb may not be a politically correct thing. We should replace that. But in the original paper that discussed this, they used the bomb. Yeah, so let me say that some people raise the question of Dirac notation. It's really just a notation. You will get used to that. So instead of writing a vector with an arrow, you would just write ket. Yeah, so we would do that a lot. I think by the time of the maybe after a month, if you still feel not comfortable, please let me know. Yeah, for this course, you don't need to take solid state physics. What I'm going to use would be elementary. Some of you, I will show you equation, but I don't require you to solve equations. For those that can be solved in a simple way, then I would use that. But for those that may be more difficult to solve, you can do verification. You can use Mathematica. You can use MATLAB. As long as you have a tool that sort of overcome the technical part, I think that's already good enough. Any other questions? Okay, maybe if not, there is a third poll, but it's about today's class because I prepare a material that I was supposed to cover really the chapter 1. We're still at the appetizers. The main dish has not yet come, but maybe give me feedback of today's class. Okay, so let's take 10 more seconds to finish the poll. Okay, so this is the result. Okay, I'm glad that I wasn't too fast and the topics were not hard. I would try to explain if there's sometimes there might be new concept that's hard to digest in the first time, but I will try to explain it in a slowly and clear way. Some of you know everything. I know that there's a large spectrum of student background, so I don't expect you to know everything in the beginning, but if you do, that's very good. And then maybe I could encourage that you could have the discussions like in the chat. If some people ask question in the chat and if you know the answer, you could also post that. And at the end, I would go over the chat and see if there's anything missing. Okay, and I'm glad some of you said you learned something new. This is also a new experience for me because this is my first time teaching online. Yeah, so, but I hope that it's a class that we do it together, that you also help one another to achieve the learning. Okay, and the homework is already posted in Blackboard. It's due next Wednesday, noon. If you need extension, you should let me know in advance. And give me feedback anytime by email or in the chat, private chat. So I guess that's it. I hope you would enjoy this course. I'm starting to enjoy as I design this course. I hope you would enjoy as well. And one reminder is that I would record this. If any of you see that the recording button is not hit, not pressed, let me know. Because the Zoom start at 2:30, that's the way it can be organized, 2:30, but the class begin at 2:40. So let me know if I forgot to record the lectures. And I guess that's it. Any questions? Okay, if not, let me end here and I will stop the recording. I hope you have a good day and enjoy, welcome back, enjoy the semester. I hope we make the best use of this difficult time, but through online learning, we can also learn a lot. Okay, thank you.
Thank you.
Bye.
Thank you.
Thank you, Professor.
Thanks.
Thank you.
Bye.
Bye.
Bye.